The rotation of a three-dimensional velocity field is measured by the vorticity omega equals the gradient crossed with the velocity field. If omega equals 0 at all points in the domain, the flow is irrotational. Which of the following fields is irrotational? So to find this, we cross the gradient with the velocity field, and we get a determinant which we calculate, and we get that the flow is irrotational because omega equals 0.
For the second v function, we do the same procedure. We find the determinant, and we calculate that omega is also equal to 0 in the second v function, so that function is also irrotational.
Recall that for a two-dimensional source, free flow velocity vector is equal to u, v, 0. A stream function psi x, y may be defined such that u equals psi y and v equals negative psi x. For such a two-dimensional flow, let zeta equal the k vector multiplied by the del operator multiplied by the velocity, or crossed with the velocity field, and let that be the k component of the vorticity. Show that the del operator's second derivative with respect to psi is equal to the del operator times the del operator psi is equal to negative zeta. So we then take the velocity field that is composed of u, v, and 0, and plug that into zeta with the del operator multiplied by the kth component of the function. And then from there, we'll go ahead and take it into the del operator second derivative with respect to psi, and plug those in, multiplying by the kth component. We multiply that resultant. And then going forward, we then solve for zeta, which is then equal to negative psi xx minus psi yy, which then gives us a resultant of the del operator multiplied by psi x, psi y, 0, which then gives us as negative zeta equals psi yxx, or psi xx plus psi yy plus 0.
We're given a function psi of xy. U is equal to the partial derivative of y. V is equal to the negative partial derivative of x. We plug those into the velocity v and plot the vector field.
For the last part, we're going to use the velocity vector that we found in part C. So first we're going to go ahead and get a vorticity function, which just means we're going to get the kth component of the velocity vector. So to do that, we follow a similar procedure as in part B and part A, where we just take the determinant of the gradient crossed with, or we take the gradient crossed with the vector, the velocity vector, and then we dot that with the kth vector, which is just 0, 0, 1. From there, we take the derivative of the vorticity function with respect to x and y and set those equal to 0 to find the critical points. We find critical points of pi halves 0, pi halves pi, 0, pi halves, and pi halves, and also pi halves. When you plug these into the function ac minus b squared, which you get from finding the second partial derivative of the function with respect to x, the second partial derivative of the function with respect to y, and the second partial derivative of the function with respect to x and then y. When you plug those in, pi halves is the only one that doesn't give you 0, so you can determine that one is a maximum. And then you have to use the boundary points, so you can use 0, 0 as a boundary point. And when you plug that in, you get negative 4, which is obviously less than 0, so you find that's a minimum. And just to verify, you can plug both of the critical points back into the original vorticity function, and you find that the vorticity function at pi halves is equal to 2, and the vorticity function at 0, 0 is equal to 0.